Hi team, we're looking at now 1.7 in our review. So thank you for showing up for your learning and reviewing all the concepts in this past unit. We're going to start with determining the points of intersection between these different functions. So I've copied them out and I write them in function notation. I like to do that because I know I'm going to be looking for when does g of x equal f of x. And that helps me set up my first line and understand why I'm doing it. And like I always say, start with a quick visualization. And I prepared one for you in Desmos, and I'm going to show you again how to do these quickly in your mind. So here's the parabola 4x squared minus 15x plus 20. We notice that it's crossing the y-axis up there at 20. So that's the y-intercept. It's opening upwards and it's quite stretched vertically. And then the last piece of information we need is this idea here, that it's crossing the y-axis at a negative slope. That is to say, if I graph the line negative 15x plus 20 down here, I'll notice that that line is tangent to the parabola at that point. It's right on top of the parabola. It's so very close to it until you see the parabola starts turning. And as the parabola starts turning, it moves away from the line. You can see there, it moves away. And if we look up, you see the parabola, its slope is only the same as that line at the moment where it's crossing the y-axis. So that's how we visualize it. Okay. Now we don't need this line for the visualization, but I'm just showing you how I use that number minus 15 to see a parabola in standard form very quickly in my mind. Then I can imagine the line 5x minus 4. I know it crosses down there at minus 4 and it's rising very quickly. So if it crosses, I bet it crosses somewhere over there. Let's take a look. Boop. Okay, it does seem to cut the parabola at 2 points. So we're expecting to find 2 points of intersection. From my quick mental visualization, I could really only tell you that it might touch once, 0 times, or twice, but if it does, it would be in the first quadrant. Okay, let's take a look at algebraically how we're going to proceed. So now I copy in my values for g of x. So I say 5x minus 4 is equal to 4x squared minus 15x plus 20. Okay, now this problem is pretty much done. Just solve for x, ha ha ha, and then solve for the corresponding y values. Okay, so how are we going to do that? Well, let's move all those g of x terms to the other side. I'm going to subtract 5x and add 4. So I'm going to add 4 over here and subtract 5x. And what I've done is I've set the quadratic equal to 0. That allows me to use either factoring or quadratic formula to solve these. Minus 20x plus 24. Okay, so this created a new function. This function basically shows me the distance between g of x and f of x at any given point. All right, so when that distance is 0, that's an intersection. So let's solve for x, and so we will have, let's say we play our x game. So I'm pretty sure this one factors. Let's find out if it factors. I want to add numbers to minus 20. Oh, first we should check and see if there's any factors that can come out as common factors. Oh, there is 4. So 0 is equal to 4 multiplied by x squared minus 5x plus 6. All right, and we can go ahead and divide both sides by 4. 0 divided by 4 is still 0. So we just want to know where does x squared minus 5x plus 6 equal 0. Okay, and that one, if it multiplies to negative 5 and adds to 6, well, like we predicted, these intersections are very close. This is going to be x minus 2. Ooh, that was weird. Times x minus 3. I should have just gone with it and made that a 3. My brain was a little bit ahead of me there. Let's keep going. All right, so now we know that x equals 2 or x equals 3, because this statement gives us the roots. X equals 2 makes that one 0. X equals 3 makes that one 0. So x equals 2 or x equals 3. And then we can use either f of x or g of x. I would recommend using this one. It's simpler to solve for the corresponding y values. So let's solve for g of x equals 5x minus 4. And we're going to solve that when x is 2. So g at 2 is equal to 5 times 2 minus 4. This is the point g at 2 is equal to 6. And then we have g at 3 is equal to 5 times 3 minus 4. This is equal to 11. G at 3 is equal to 11. So it looks like, therefore, the POIs, the points of intersections, are 2, 6, and 3, 11. See, they touch pretty close. That's why, like, from my quick visualization, I couldn't really tell you how many times they were going to touch. But Desmos is a really good visualization. So let's see. Here is the point. Let's zoom in. See, its vertex is real weird, right? But it's got a nice point of intersection there. 2, 6. We found that. And then up here, 3, 11. Oh, look at that. The algebra was perfect. Cool. Let's do the next one. B. All right. I have a feeling we're going to need quadratic formula for this one. Okay. Let's zoom in a bit and let's get started. So I'm just going to copy out my stuff. Spare you watching me. So we copied out the two functions. I put them in function notation because I always like to start with the line g of x is equal to f of x. Substitute in minus 3x minus 5 is equal to negative 2x squared plus 9x plus 9. All right, let's visualize. The quadratic crosses up here at 9. It's opening downwards, and it has a positive slope. So it's looking something like this, right? Okay, it's looking something like that, this quadratic. And then the minus 3x minus 5, well, that's crossing down here. And it's got a slope of minus 3, so it's something like that. All right. So yeah, it's going to have one intersection way out there and one intersection back here somewhere. Okay, so I'm predicting two intersections. It's pretty clear this is going to definitely have two intersections because we got a point that's inside the parabola, so it's going to hit twice. So let's do our work here. We're going to do the algebra work to find those points that we quickly visualized. Plus 3x plus 5 to both sides, plus 3x plus 5. All right, so our next line is 0 equals negative 2x squared plus 12x plus 14. Will this factor? Well, let's see. We want to be able to multiply to negative 28 and add to positive 12. Yeah, gosh, we can do that. We can do that with 14 and negative 2. Okay, 14 and negative 2 will do it. Oh, that's too bad. I thought we were going to get to use quadratic formula here. Yeah, what I did was I found that I can multiply to negative 28 and add to positive 12 with the numbers positive 14 and negative 2. Okay, I got the negative 28 from these two numbers here. Multiply them together. All right, so we go like this. 0 is equal to negative 2x squared minus 2x plus 14x plus 14. So I split up that negative 12x into two terms. And then we have 0 is equal to, well, negative 2x can factor out of that. And it gives me x minus 1. And then 14 can factor out of that. So 14 can factor out and give me x plus 1. And I see I could have taken out a factor 2 there. Oh my goodness, that would have made things easier, wouldn't it have? Okay, so then 0 is equal to negative 2x plus 14 multiplied by x minus 1. Take out the factor 2 eventually. We got there in the end, everybody. Factor out negative 2, and then we have x minus 7 times x minus 1. I'm a little bit surprised by that both of my intersections are positive x values. Huh. But we'll look in Desmos and see where my thinking is not quite right in just a moment. Maybe I have a sign error. But anyway, let's try them. I'm pretty sure that this must be right. Or I'll go do some investigation, then show you Desmos. Yeah, so quick Desmos visualization just confirms my quick visualization that one of our roots should be negative and one of our roots should be positive. I too make sign errors. Let's go find my sign error. This is x plus 1, and I wrote x minus 1 there. So that was my error there. So you see this should have been x plus 1. When I factor out the negative 2x from both of these, I get plus 1, negative 2x. Okay, when I divide that by negative 2x, that's the negative 2x. That gives me positive 1. So this is positive 1, positive 1. Because my visualization, that's correct. This is a negative 1x, and then this is positive 7x. So yeah, the direction of my visualization helped me find that sign error and avoided me making costly errors for time. So useful, right? Start with these little visualizations. I really recommend it. So we know that x is equal to negative 1 or x is equal to 7. Okay, let's find the values. So g of x was equal to negative 3x minus 5. And we're going to use that and substitute these two values of x to find the values of y. So g at negative 1 gives us negative 3 times negative 1 minus 5. This is negative 2. And g at 7 is equal to negative 3 times 7 minus 5 equals negative 26. So therefore, the two POIs are negative 1, negative 2, and 7, negative 26. Cool. All right. So that matches what we were seeing over here. This is negative 2, negative 1. Sorry, negative 1, negative 2. It was actually a little down there. And this one is way down there and way out in the positive x, negative y. So that was the value of having one of those quick visualizations. All right, now this next question is a little bit challenging. For what value of b will the line this be tangent to the parabola that? Okay, so let's take a look at that. If we have a situation where a line is tangent to a parabola, that means it touches the parabola at one and only one point. So that means that when we do like f of x is equal to g of x, that there should only be one solution for x. One x only. So after we've simplified these things, the discriminant should be 0. I'll show you how we do this one. Okay, we're going to use the properties of the discriminant. We know that the discriminant can tell us the number of solutions, either 2, 1, or 0. We only have one solution to the quadratic equation when the discriminant is equal to 0. So let's go for it. Okay, we have f of x is equal to 3x squared plus 4x minus 1, and g of x is equal to negative 2x plus b. Okay, set them equal to each other. Negative 2x plus b is equal to 3x squared plus 4x minus 1. Okay, we're going to subtract. We're going to add 2x to both sides. We're going to subtract b, this number we don't know yet, from both sides. And then we're going to have a new line that's equal to 0 is equal to 3x squared plus 6x minus 1 minus b. Okay, so for this to have one and only one solution for x, you could use your knowledge of perfect square trinomials here to find a solution pretty directly, or you could use the discriminant. let's make a little copy of our numbers for the quadratic formula. A is equal to 3, B is equal to 6, and C is equal to -1 minus B. Notice that once we know B, together those would be the number C. Okay? And we know that we want one and only one solution here. So the discriminant, b squared minus 4ac, that should equal 0. All right, so let's do that. Let's use that. Okay, I'm going to do it down here. B squared, we're going to say 0 is equal to b squared minus 4ac. And we have now one equation and one unknown. B squared is 6 squared minus 4 times 3 times 1, -1 minus b. Just substitute in for 4ac, and then let's figure it out. 0 is equal to 36 minus 4 times 3. This is minus 12 times -1 minus b. Okay, so let's isolate and simplify everything away from b. We could even multiply this in. Sure. I mean, I can spot the solution now, but maybe you can't. You probably can't because you don't have as much practice as I do, which is fine. 0 is equal to 36 plus 12 plus 12b. Okay, 0 is equal to 48 plus 12b. Subtract 48 from both sides. -48 is equal to 12 multiplied by some number b. Divide both sides by 12, please. -4 is equal to b. There, b is equal to -4. All right, so let's visualize it in Desmos. Okay, we're going to look at this in Desmos and see if we're right. Okay, here's the situation where we have our quadratic. F of x is 3x squared plus 4x minus 1. And our linear equation is minus 2x plus b. And I set b as a slider. Looks like b needs to go down, 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 down. Oh, look at that. When b is -4. Oh, look at that. When b is -4, there's one and only one point of intersection. I can zoom in. Look at that, everybody. That's the magic of the discriminant. Isn't that cool? Isn't that just so cool that we can use our knowledge of the quadratic formula and the discriminant to solve situations like this? It's great. I love it. Okay, so last question. Do all linear quadratic systems result in a solution? Justify your answer using a real-life example. Okay. No, all linear quadratic systems do not result in a solution. For example, if b was less than -4, it's going to touch 0 times. Okay, now that's not a real-life example. One real-life example would be if I have a laser pointer, and I'll create a brief visualization. Here, okay. So a submarine located 1 meter under the water fires up at some kind of torpedo that goes blorp and comes out of the water, rises 2/3 of a meter, and goes down back into the water at the point 10. Okay, I just use the quadratic that we had. Like this. And then I say, when does that get 45 degrees above the horizon? So I have a laser pointer that I'm using there at 45 degrees, and I wonder, when does this torpedo get there? It never gets there. It doesn't go very high, okay, because it comes out of the water out there, and it never achieves an angle of 45 degrees to the horizon. So it just doesn't have a solution. So that would be one kind of like real life example that we might consider there. Okay. So anyway, if you have any questions about linear quadratic systems, absolutely send me an email. Screenshots are great, or specific questions in the textbook are great. It helps me help you better. And thank you again for showing up for your learning. I hope that you have a great day, and I hope to see you again very, very soon. Bye for now, everybody.